My name is Ed Lawson. I'm from Naval Research Lab. So I have the pleasure of being the first speaker in the very last session here. So I am appreciative to everybody that's still here. This is my first time tonight since pre-pandemic stuff. So grateful to the organizers and to all of you for great talks during the week. Eventually you'll see my slides, but I'll just talk through it anyway. Maybe. So the real goal of this project right here is that I'm trying to get my autonomous robot. He's a little quadruped named Byte. It's a little Boston Dynamics robot. It's about yay tall, that big. We're interested in getting this robot to work as a collaborator for shipboard maintenance types of tasks. This would be really helpful if I had some slides to show you nice, pretty pictures and stuff for this type of thing. So some of these tasks that we've been looking at recently is this idea of putting the robot on board a ship to do these maintenance tasks. So one of these things that during these tasks, they get these little cards called these MRCs, right? MRCs are written towards the level of somebody that has like a high school education. That's not really super technical. It includes things like the tools that you need to perform the task and the step-by-step goals to perform some task. So the fantasy would be to be able to give this just to Byte and have Byte be able to perform all of these tasks for us. I wish I were presenting those results here. I'm not. So this is kind of something that we're working towards a little bit here. So what I'm working on here is this idea of using the sigma delta networks to do arm positioning. So Byte has a little, and again, pretend that you had a picture of this. Has a little arm on the top of it, and I can extend the arm and I can move it around to do basic things. So one of the first things that we're looking at for this is, you know, if I'm on board ship, if I'm doing slam or something like that, I'm getting towards these electrical panels. The ships are rocking back and forth, and I can't always guarantee that I'm going to be in the same spot every single time. So I need to make sure that I am able to be tolerant of little errors. So if I'm off a little bit or the angle's off a little bit. So I need to be able to position the arm in such a way that I can get to the center-ish of my electrical panel. So that's one of the tasks. The second one that I've been working on kind of more recently is this idea of using the same type of approach to have Spot fetch me tools. So if I were to say, Spot fetch me a hammer, that it could go walk over to a pegboard, pull the hammer off the pegboard and bring it back to me. This is something that I did not report in the paper, but it's something that, so I don't actually even know where my laptop has gone at this point. Said that I didn't report on these results in the paper, and it's not really a complete solved task, but it's something that I'm going to show you a little bit of a teaser towards, maybe towards the end, if I show anything at all. So is this coming back anytime soon?
They're trying to put the presentation on the separate computer.
Oh, okay. There's a lot of videos. That's going to take a little bit. Okay, so moving right along. So this would be my second slide now. So the ideas with the sigma delta networks. Why did we get involved with sigma delta? So in Intel, whoa, hey, I've got a presentation. This thing control it? Maybe? This one? Which one? Ooh. Oh, this one. Okay, fantastic. I may need help playing videos at some point, but okay. So that's the first slide. Hey, that's Byte right there. So that's the picture I promised you. So second slide here. So like I said, I'm trying to position the arm to move the arm around. So this is kind of sort of like object detection in the sense that if I were looking for a hammer on the pegboard, I could just do object detection. But it's not really object detection that I'm trying to do. I'm trying to find a good point at which that I can move the arm to and grab the hammer, let's say. So there's sort of a controls problem here a little bit there too. I need to grab just a certain spot on the hammer and I need to manipulate it in such a way to get it off the pegboard. Joe Hayes actually has all of the answers for that, and he will be speaking next and telling me about all of the answers for that. So that there's an interesting controls problem. I'm not talking about those at all. What I will propose here is this network that I'm calling ARMNet to position the arm. So ARMNet is basically just a simple network that you give it an image that's taken from the gripper cam, and it predicts how the arm should move to get to the next position. So up, down, left, right, or stopping. The idea behind this is pretty simple, is that this is kind of an OODA loop. So I'm going to observe what the gripper cam is doing. I'm going to think about what it is that I should be doing next. I'm going to decide on that, and I'm going to take the actions. So sigma deltas, why sigma deltas? So when Intel announced that, I was naturally quite interesting, because this is a perfect problem for sigma delta networks. The image doesn't change all that much as I'm moving my arm through the scene. It shouldn't change that much unless I'm taking very big steps. So this is pretty much the problem that these things were designed to solve. So what I'm using here is a deep Q learning approach to solve this problem here. A lot of the previous work with sigma deltas have used the supervised learning. I'd like to convince you that my approach is slightly more sensible for this particular problem here. And you will see why shortly. This is just a little bit of related work. I won't spend a whole lot of time here. I'm not going to talk about some of the related work on deep Q learning at all. There's a whole ton of it, and it's as good as advertised. Sergey Levine and Peter Abel have lots of good papers on these things. Some of the more recent contributions have been improving these to try different techniques, using vision transformers, pre-training, that type of stuff to make these things a little bit more robust. I'm not going to really spend a whole lot of time on that. There's great tutorials online now. I do want to spend a little bit of time talking about these sigma delta networks. Honestly, there's not a whole ton of work that I have found on using this for vision problems. One of the earliest one is this work by O'Connor and Welling. This was at iClear in 2017. They created this data set that they called their temporal MNIST, which is confusing because I think this community also has a different data set they call temporal MNIST, but this is a different temporal MNIST. They arranged the MNIST data set so that the letters sort of looked like they were very similar over time. So there's lots of redundancy. So they demonstrated that they could solve the temporal MNIST with their version of sigma deltas, and they could reduce power by at least an order of magnitude. They didn't actually report numbers, which is disappointing to me. But it's noteworthy that they didn't do anything with images or sequences. PilotNet, which is not really technically a published work, but it's in the Lava tutorial, so I thought I'd mention it because how many people have gone through the PilotNet tutorial here? Nobody? One, two. Okay, well, the Intel guy, of course. So he'll probably be showing you more about this tomorrow, would be my guess. So they had a supervised learning task where they're trying to control the steering wheel of a car, and you give it sequences of images that show how you need to turn the steering wheel in order to position it correctly. They have a lot of data for this problem. It's 45,000 training images, and it's all completely supervised. So before I get on there, there's a video there if you could play it. I'm not sure I can play things. Like I said, sorry, there's a lot of videos here. So before I get exactly to some of the details on how I'm doing the reinforcement learning, I'm going to start with the supervised learning problem. There you go. So this is ARMNet. It's a really, really simple network here. There's 3 convolutional layers, there's 2 dense layers, and there's an output layer. This is all wrapped with the sigma delta approach. So you have the sigma decoding on the input and a delta encoding on the output. Basically what it does is that if you could play that video one more time. If you see something that looks highly redundant over time, basically what it does is it makes it sparser. It says that this looks exactly the same as it did in the last frame. So I don't need to propagate it forward. So what you end up doing is you get this massive energy saving. I think you probably also get slightly better answers because information that was seen in previous frames can also get propagated forward through time as well. So this is pretty much all there is to that. So I've been teasing the whole why my reinforcement learning is better than the supervised learning approach to this. And this is kind of why. So the first task that I looked at this was this idea of how can I take my robot and how can I center it on the electrical panel? When I say center on the electrical panel, if I had a laser pointer here, that would be even better. No? Well, whatever. There's a thermostat. Oh my goodness. Okay, so that's not the laser pointer, that's the break my presentation button. Oh, here we go. So when I say center of it, there's a thermostat that's kind of in the top center part of that. It's the little thing with a little red and blue circle. When I say center, what I'm trying to do is I'm trying to move my arm to be positioned right on top of the little thermostat. What I actually did do to start off with this is I put my robot in front of the thermostat, and then I ran sequences where it was moving from all different possible locations up to the thermostat. It took a while, and it was kind of a pain in the butt to collect all that data. So, and that worked relatively well. But what happens if I want to move my robot arm now to the fuses? Now I have to do this process all over again with moving my robot arm over to the fuses rather than to the thermostat. So I think this is kind of a waste of time. So what I'm proposing to do here instead is I collect really, really high resolution images of the electrical panel and of the pegboard on the left here too. Actually, if you look at the electrical panel, there's a little bit of image stitching between the top and the bottom so that I could get it to be the proper resolution. And then I simulate what the gripper cam might see when it's positioned at a particular position in front of the electrical panel and at a certain distance. And that is simply how I am just generating as much training data as I want. So this is kind of sort of in simulation data, but it's not really. It's just the realistic data that it's being cropped. So I said some of this stuff already. I start off with this basic observation here that as I move my gripper cam arm through the image, there's just a lot of wasted computation. I could make a decision at each individual frame, but it's just not necessary. The images, they change so very infrequently, and it's not necessary to process the same data over and over again. Basically, if you see like the thermostat or the fuses here, and you move your arm up a little bit, you're still going to see the thermostat and the fuses. So rather than process that data all over again from scratch as if I'd never seen it before, that data just gets propagated forward. So you don't actually have to waste the time doing those things. So what you end up getting is you get the same answer with far less computation. It's also interesting to note that some of the earlier work on this, they actually showed in a theoretical proof type of a way that the sigma delta networks are also functionally equivalent to a convolutional network if you structure them in a very specific way. So the answer is that no matter how you look at this, you can get the same answer with far less computation. So this just puts it a little bit more formally. So you have the sigma decoder around the dendrite with the input, the delta encoder around the axon, the output. This is for each neuron in the system. So for each neuron in the system, it gets to take advantage of these things. Mathematically, you have there. So the delta neuron, it starts out with an initial value of 0. At each time step, it takes the initial value and subtracts it from the previous value. The sigma neuron kind of does the opposite. It just incorporates new data over time. So that's kind of the sigma delta bits. So deep Q learning. So I'm sure if anybody's taken an intro to AI course, you've seen stuff about Q learning. You probably know a little bit about deep Q learning. Feel free to zone out if this is all background material to you. So rather than taking the annotated sequence, what I want to do is I want to generate sequences that are based on the predictions. So as I move my arm and my arm takes a predicted movement, I'm just going to generate what the gripper cam might see if it took that particular movement. This uses just a single high resolution image. So I can do this with just taking a very high resolution image of my pegboard, and I can train these networks. So Q learning, so this starts with this Q table that builds an estimate of the expected reward of performing an action A in state S that results in this policy that's basically a greedy policy that just takes the best answer at every time step. Deep Q learning, it gets to be difficult to summarize an image in a state. So the deep Q learning, does basically the same thing, but now the Q table is embedded inside the network where you have a single neuron that's associated with each action, and your deep Q network should be able to predict the expected reward from performing each one of those actions. So you train this is with the Bellman equation here. So the expected reward from performing a particular step combined with the expected reward from future steps. And this is discounted by some discount factor gamma. And the deep Q network, the loss is basically the difference between the Bellman equation and what it's currently predicting. There's lots of optimization, and there's a citation to Sergey, although there's some of them in other works there. So one of them is to take this replay memory. So rather than performing every action, you store the actions that you've seen in the past, and you store those actions for sampling and training your network in the future. Another is that things get a little bit more stable if you train a policy network. That is the Q primed is stored separately and updated very slowly. So these things help tremendously. All right, so that's all the boring stuff. So now we can get to kind of start to get to some of the fun robotic stuff. If you could play that video, that would be helpful. Sorry. So if I were to start at a point P, the state S is basically just the image that's centered around that point. So each one of those actions, there you go, thank you. You can kind of play that a few times just so everybody can see the pretty pictures. The images are better quality than that. It was kind of the bad codec coming from that thing. So you play a game here, you take a step based on what the network says I should be doing, and you repeat until either byte has found the target or some time limit has been exceeded, and there's some rewards for finding the right thing and some penalties for going in the wrong direction and such. That's good, thank you. Okay. So now I'm going to talk a little bit about the experimental results. So if I were to start at some point, I want to center the arm of the robot on the electrical panel. These are kind of a few images here. So one of the things that we've done here is that we move the arm to the center of the electrical panel, and then we look in certain places for other components, and then we'll extend the arm fully in order to be able to clean those things. Not pictured in this image right here is there's a vacuum and a hose that gets connected over these things, and I can actually vacuum it to clean the electrical panel. So some of the other bits that I can do here is it can look for things like fuses that have been blown, anything that looks a little funny, so things that have been browning out, electrical wires that look like they need to be replaced. These are all certain tasks that byte can perform while looking at the electrical panel. So I'm going to show results in simulation for this particular task. And then I'm going to show actual fun results for later stuff. So if I simulate a distance of about 50 centimeters, the image that you look at is about 40 centimeters by 40 centimeters or so. And it does a great job. It finds it pretty much every single time. So the blue circles are where it ended up going. One of the interesting things that I saw out of this particular task is that it does not always necessarily take the best route to the center of the electrical panel. Sometimes if it starts off in the weird gray area on the bottom, sometimes it'll wander around until it runs across something that it knows, like the fuses, and then it will start to take a path from there. I think it's possible if you were to switch up the reward function that this would maybe kind of change that behavior, but I kind of thought it was a cool behavior, so I'm not going to change it. So, all right, so this is something that I have honestly been working on maybe only the last couple of weeks. So the idea is that if I can start from any random point in that image and find the center of the electrical panel, can I kind of do the opposite thing with the pegboard? So I start on the center-ish of the pegboard, and now I want to move it around in order to pick up each one of those tools. So these are small modifications over the things that I showed you before. I'm adding a pickup neuron, so it actually says when it should be grabbing the pickup neuron. During training, I actually gave it a reward for selecting the pickup neuron, and I did not penalize it for doing it when it shouldn't. And what I did is I added just 6 control neurons to the very last dense layer. So now it's the same last dense layer plus it's 6 neurons. It's one for each one of the 6 tools on the pegboard. An image would have been helpful here, but take my word for it. There's 6 tools on the pegboard. And so I set the neuron to 1 when I want to pick up that particular tool, and I set it to 0 when I don't want to pick up that particular tool. And grasping, I should give credit where credit is due. This is all Boston Dynamics SDK. Their SDK is actually pretty awesome. If you specify the point at which you want to grab the tool at, it computes how it might move around to that particular tool. It has a depth camera on the front, and it actually does the grasping bit for you. So this is the video, which I'll have them play in just a second. But oh, he's just going to play it now. All right, so it takes it a little bit to move around here. I'm kind of running it a little bit slow because I'm watching the network output here. It does not work perfectly. Sometimes the grasping code works rather imperfectly. Sometimes it charges into the pegboard, and so that's why I'm running it kind of slow. There's some bugs to be worked out here, and I'm not claiming that I've solved this problem quite yet. Well, there you go. It kind of moves the arm over to the hammer and it grabs the hammer off of the pegboard. And that's me stopping. Yeah, thank you. Woohoo! I felt rather accomplished when I took this video. I had to include this here. I'm not claiming that I've solved this problem, but it's kind of the direction that I think you could go with this type of thing. I think there's lots of other similar type of tasks that you could do here. The fantasy is that I could use somebody's speech to their spikes and tell the robot that I want to go grab the hammer off the pegboard. The robot uses the bat slam to, not a bat slam, the rat slam to wander around the environment to find the pegboard, and then grabs the hammer off the pegboard and it brings it back to me. Or it just does the work for me. That would be fun too. I hope I've convinced you that deep Q learning can be an effective way to use the sigma delta networks. ARMNet, I think you could use this type of approach to solve any variety of sort of arm centering type of problems. It's kind of a cheap way to get around object detection, which is a rather expensive algorithm and a rather big network. So the evaluations I've shown a little bit on hardware and a little bit in simulation. I'm grateful to my collaborators here, some of which are in the room here. Joe Hayes and Sam is back there as well, and my collaborators at NRL that I'm not talking about because they're not here. So I think there's lots of things that you could do with this type of thing. I would love to replace the grasping with something that's a little bit more sensible. I showed you an example how I was grabbing the hammer off of the pegboard. If I were to grab some of the other tools, you need to sort of lift it up in just a certain way in order to get it off the pegboard. And also, if you were to grab the screwdriver by the end tip, that's not really going to do very much at all because it's not a whole lot of stuff to grab it by. So you need a smarter way to grab things. I think you could use a learned policy for that. And again, Joe has solutions for that. So there's many other tasks that you could do with deep Q learning and this type of approach. Some of these are really a lot bigger, like replacing a fuse, opening and closing the fuse box, looking for wire problems, and pressing buttons, grabbing handles, any of those types of things too. Oh, and I guess that's the last slide. So that's it. I am done talking.